This is a look at the base compute costs for Google's new Gemini 3.6 Flash. It runs at $1.50 per million input tokens and $7.50 per million output tokens. Historically, scaling an AI model meant accepting a strict mathematical trade-off. If you wanted higher reasoning capabilities and precision, you had to pay a premium in latency and token cost to run a heavier architecture. Google's 3.6 Flash breaks that correlation. When measured on the Artificial Analysis Index, it actually consumes 17% fewer output tokens than the previous 3.5 iteration. At the exact same time, its baseline capability scales up. On the DeepSWE benchmark, output precision jumps from 37% to 49%. When a model generates fewer unwanted code edits, it requires fewer execution loops to arrive at the correct answer. You are paying less per token and using fewer of those tokens to get a better result. This requires engineering teams to shift how they calculate overhead. The relevant metric is no longer raw token pricing, but the total cost per agentic task. Cost per million tokens only measures the price of the pipeline. Task-based pricing measures the efficiency of the model actually navigating that pipeline from the initial prompt to final execution. The economics of deploying AI agents at scale are changing. The tier designed for high-volume, low-cost operations is actively driving down its own resource consumption while executing more complex logic. This coordinate plane maps cost against capability. 3.5 Flash sat in the middle, balancing reasoning with costs, but struggling with complex workflows. 3.6 Flash optimizes existing resources, applying a sharp vector shift that pushes the node toward higher capability and lower costs. This shift is primarily driven by how the model processes complex prompts. It simply requires fewer internal reasoning steps to reach a valid conclusion. Secondarily, it relies on fewer tool calls. It doesn't ping external scripts or databases as often to successfully complete multi-step agentic workflows. To support this, computer use is now integrated as a native, built-in client-side tool that developers can access directly through the Gemini API and Gemini Enterprise. By streamlining its reasoning process and native tool access, the model achieves higher output precision and actively avoids the looping errors that drain compute budgets. Evaluation data shows how improvements map to real-world tasks. In DeepSWE, token consumption drops by 65%. On MLE Bench, performance scales from 49.7 to 63.9. OSWorld-Verified scores climb from 78.4 to 83.0, and GDPval-AA pushes from 1349 to 1421. In a production environment, these margins matter. They dictate a system's ability to reliably execute large-scale, multimodal enterprise tasks, like parsing thousands of financial documents, analyzing charts, and drafting synthesized reports. Google is also deploying a specialized variant called 3.5 Flash Cyber. It's a highly tuned, limited-access model designed specifically to detect, validate, and patch code security vulnerabilities within CodeMender. Across the board, these models are shipping with strict frontier safety safeguards. They are actively hardened against chemical, biological, radiological, nuclear, and offensive cyber misuse, making them highly resistant to jailbreak attempts. The data shows that the mid-tier, high-volume workhorse models are operating with the reliability required for automated, enterprise-grade knowledge tasks. Certain engineering pipelines like agentic search and massive document processing will always hit a hard ceiling on throughput. They require raw speed above all else. Gemini 3.5 Flash-Lite is the targeted solution for these low-latency constraints. As the fastest model in the 3.5 series, it processes a sustained 350 output tokens per second. It supports this throughput with highly compressed pricing, 30 cents per million input tokens and $2.50 per million output tokens. Developers can actively configure the model's thinking levels to match the exact volume and complexity of the workload they are routing. For raw, high-volume tasks, setting a minimal thinking level maximizes execution speed. For multi-step sub-agent loops, engaging a higher thinking level allocates the necessary processing power to complete the sequence. By compressing the latency and the token cost, massive data synthesis pipelines that were entirely cost-prohibitive last year are now economically viable. There is a persistent assumption in machine learning that highly quantized, light models are too constrained to handle complex reasoning. This directly contradicts that assumption. On SWE-Bench Pro, 3.5 Flash-Lite scores 54.2, overtaking the heavier Gemini 3 Flash at 49.6. The data repeats on OSWorld-Verified. The sub-dollar Lite model hits 74.0, while the older 3 Flash base model trails at 65.1. A heavily optimized sub-dollar model is now outperforming a larger, more resource-intensive foundation model in direct task-based evaluations. These agentic execution scores are made functionally possible because Flash-Lite also includes the same built-in computer use tools as the standard Flash tier. When orchestrating workflows, scaling up raw parameter counts is no longer the guaranteed path to better performance. Targeted, hyper-efficient tuning is yielding higher returns. These benchmark inversions force startup founders and engineers to rethink their system-level architecture. In traditional model routing logic, systems are designed to automatically push complex user requests to a massive, expensive frontier model to ensure a correct answer. Modern engineering is moving in the opposite direction. Routing algorithms can now dissect a complex prompt and assign the subtasks to a swarm of small, hyper-fast, highly specialized nodes. As the capability gap between light models and legacy giants continues to close, automated routers will mathematically favor the swarm approach to preserve compute budgets. Using a heavy frontier-class model as the default starting point for standard agentic loops is simply a misallocation of resources. At what point does reaching for the most expensive models stop being the default engineering decision and start becoming an architectural liability? We are Synthiac Labs, bridging the gap between theoretical research and working prototypes.